The empty space right in front of your face is not empty. Right now, billions of particles are appearing and vanishing in the void between your eyes and this screen, and they are doing it so fast that no instrument on Earth can catch them in the act. This isn't a theory. It's one of the most confirmed predictions in all of physics, and it gets so much stranger from here. Fact number 1, empty space is boiling with invisible particles right now. According to quantum field theory, the most precisely tested scientific framework in human history, what we call empty space or the quantum vacuum is not nothing. It is a seething, roiling ocean of energy. Every single point in the vacuum, even the deepest void between galaxies, is constantly fluctuating. These fluctuations spontaneously generate pairs of particles, one matter particle and one antimatter particle. They appear from literally nowhere, exist for an almost incomprehensibly short time, and then smash back into each other and annihilate, releasing the energy they borrowed and vanishing without a trace. Physicists call these virtual particles. The timescale? We're talking anywhere from 10 to the power of -21 seconds to 10 to the power of -44 seconds. Those are timescales that make a billionth of a second look like a geological epoch. And this is happening everywhere, all the time, with zero exceptions. The vacuum is not silent. It is screaming at a frequency no ear can ever hear. Visual note, animate a color-coded infographic showing a flat vacuum field, then ripple waves across it in bright electric blue and gold to represent fluctuations. Pop particle-antiparticle pairs as labeled dot pairs appearing and collapsing. Fact number 2, Heisenberg's uncertainty principle is why they can exist at all. You might be asking, how can something come from nothing? Doesn't that violate conservation of energy, one of the most sacred laws in physics? Here's where it gets gloriously weird. Werner Heisenberg's uncertainty principle, formulated in 1927, says that the more precisely you know the energy of a system, the less precisely you can know it over time, and vice versa. Written mathematically, it states that the uncertainty in energy multiplied by the uncertainty in time must always be greater than or equal to the reduced Planck constant divided by 2. That's roughly 5.27 times 10 to the power of -35 jouleseconds. What this means in plain language is that the universe has a built-in tolerance for energy loans. For incredibly short windows of time, the universe literally cannot tell whether energy conservation is being violated. Virtual particles exploit this loophole. They borrow energy from the vacuum, exist for just long enough that the universe's accounting system can't catch them, and pay the debt back upon annihilation. They are, in the most literal sense, the universe cheating at its own rules, and getting away with it every single moment of every single day. Visual note, show a clean infographic of the Heisenberg equation with variables highlighted in contrasting colors. Animate an energy loan diagram like a bank ledger with a very short repayment window illustrated on a timeline. Fact number 3, the Casimir effect proves virtual particles push things in the real world. Skeptics love to say virtual particles are just a mathematical trick, convenient fiction that helps equations work out. But in 1948, Dutch physicist Hendrik Casimir made a stunning prediction. If you place two uncharged, perfectly conducting metal plates extremely close together in a vacuum, we're talking separations of less than 1 micrometer, which is 1/1,000,000th of a meter, those plates should be pushed together by an invisible force. His reasoning? Virtual particles exist everywhere in the vacuum. Between the plates, only virtual particles with wavelengths small enough to fit in that gap can exist. Outside the plates, all wavelengths are permitted. That imbalance in virtual particle pressure creates a net inward push. This was experimentally confirmed for the first time by Stephen Lamoreux at the University of Washington in 1997, to within 5% of Casimir's original prediction. In 2001, Umar Mohideen and Anushri Roy refined the measurement to within 1% accuracy. Two uncharged metal plates in a vacuum, pushed together by particles that technically do not exist. If that sentence doesn't rewire your brain, read it again. Visual note, diagram of two flat silver parallel plates with labeled gap measurement, arrows showing virtual particle density outside versus sparse density inside, resulting in a net inward force vector. Use clean, academic engineering diagram style. Fact number 4, virtual particles give the electron a slightly wrong magnetic strength. Here is how precisely quantum field theory, and by extension virtual particles, has been confirmed. Every electron has a magnetic property called its magnetic moment, often expressed as the G factor. Classical physics predicted G equals exactly 2. But virtual particles constantly surrounding the electron interact with it in tiny ways, nudging that number. When physicists calculate the electron's G factor using quantum electrodynamics, which fully accounts for virtual particle interactions, they get a value of approximately 2.00231930436256. When experimentalists at places like CERN and Harvard's electron G factor lab actually measure the electron's G factor in the lab, they get 2.00231930436082. That agreement is accurate to within 12 parts per trillion. To put that in perspective, it is equivalent to measuring the distance from New York to Los Angeles, roughly 4,500 kilometers, and being accurate to within the width of a single human hair. This remains the most precisely verified prediction in the entire history of science. Every decimal place of that agreement is a vote of confidence from the universe that virtual particles are real in every way that matters. Visual note: display the two numbers side by side in large font, highlighted in green for matching digits and red only for the differing final digits. Show a comparison infographic, New York to LA distance versus a hair width callout. Fact number 5. Virtual particles are slowly evaporating every black hole in the universe. In 1974, Stephen Hawking combined quantum field theory with general relativity and arrived at what many physicists call the most important theoretical discovery of the 20th century: black holes are not permanent. Here's the mechanism. Near the event horizon of a black hole, the point of no return, virtual particle pairs constantly pop into existence just like anywhere else. Normally they annihilate immediately. But right at the horizon, something extraordinary can happen. The black hole's immense gravitational field can provide just enough energy to promote one of those virtual particles into a real particle. That real particle escapes into space as genuine radiation. Its partner falls into the black hole. To conserve energy, this means the black hole has to lose mass equal to the energy of the particle that escaped. Over time, and we're talking timescales so vast they make the current age of the universe look like a snap of the fingers, even a stellar mass black hole will radiate away every last bit of its mass and vanish in a final burst of gamma rays. The temperature of this Hawking radiation for a solar mass black hole is approximately 60 nanokelvin, that's 0.0000006 degrees above absolute zero, so cold it will never be detectable with current technology. But the math is airtight. Virtual particles are literally unmaking the most extreme objects in the universe, one borrowed quantum at a time. Visual note: animated infographic showing an event horizon as a curved glowing arc, a virtual pair popping into existence straddling the boundary, one particle escaping upward as a labeled real photon arrow, one falling inward. Use academic diagram style with color-coded energy states. Fact number 6. The entire mass of a proton is mostly made of virtual particles. You learned in school that a proton contains 2 up quarks and 1 down quark. That is technically true but wildly incomplete. Those 3 quarks, called valence quarks, account for only about 1% of a proton's actual mass. The remaining 99% comes from the kinetic energy of the quarks sloshing around, and crucially, from a perpetual storm of virtual gluons and virtual quark-antiquark pairs constantly flickering in and out of existence inside the proton at every moment. These are called C quarks and they were confirmed through deep inelastic scattering experiments at SLAC, the Stanford Linear Accelerator Center, beginning in the late 1960s and 1970s, work that earned Jerome Friedman, Henry Kendall, and Richard Taylor the Nobel Prize in Physics in 1990. So when you hold your hand up and look at it, the atoms in your hand have nuclei made of protons, and those protons are 99% the dynamic, seething ghost energy of particles that don't fully exist. You are looking at a hand that is almost entirely made of virtual nothingness. Your own body is mostly an illusion supported by borrowed quantum energy. Visual note: show a proton cross-section infographic. Pie chart: 1% valence quarks in solid color, 99% labeled virtual C quarks and gluon energy in a swirling gradient. Compare to a visible iceberg diagram analogy, small tip visible, massive portion hidden. Fact number 7. Virtual photons are the entire reason magnets stick to your fridge. Every force you have ever felt in your entire life, every push, every pull, every time a magnet snapped to a surface, every time two electrons repelled each other, has been mediated by virtual particles. In quantum electrodynamics, the electromagnetic force is not some invisible field reaching through space like a ghostly hand. It is actually the constant exchange of virtual photons, force-carrying particles that can have masses and energies completely forbidden for real photons, again because of the Heisenberg energy-time loophole. When two electrons repel each other, they are, in quantum field theory's language, lobbing virtual photons back and forth like a game of catch. The momentum carried by those virtual photons is what we experience as a repulsive force. This framework was developed by Richard Feynman, Julian Schwinger, and Sunidhiro Tominaga, who shared the 1965 Nobel Prize in Physics for exactly this work. Feynman's diagrams, the famous Feynman diagrams you've probably seen scrawled on physics textbooks, are literally maps of virtual particle exchanges. Every magnet on every fridge in the world is working because of particles that technically cannot be directly measured. The entire macroscopic world of forces is a collective hallucination generated by virtual quantum messengers. Visual note, clean Feynman diagram infographic, two electron lines with a labeled virtual photon wavy line between them. Color code, electrons in blue, virtual photon in yellow with a V badge marking it as virtual. Add a fridge magnet icon connected by a dotted line to the diagram to tie abstract to every day. Fact number 8. The vacuum energy of virtual particles may be the most catastrophically wrong prediction in physics history, and nobody knows why. Save the best, and most terrifying, for last. We know virtual particles contribute energy to the vacuum. Quantum field theory lets us calculate how much vacuum energy there should be. When physicists do this calculation and then compare it to the actual measured vacuum energy density of the universe, which cosmologists can infer from observations of the universe's accelerating expansion and the cosmological constant, they find a disagreement so grotesque it has been called the worst prediction in physics. The theoretical calculation overestimates the observed vacuum energy by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. To give you a sense of scale, the total number of atoms in the observable universe is only about 10 to the power of 80. The discrepancy between theory and observation is a number larger than the count of every atom in existence squared, and then multiplied by another billion. This is called the cosmological constant problem, and it has been called the greatest unsolved problem in theoretical physics since 1989, when Steven Weinberg first formalized the crisis. If virtual particle energy worked the way our best equations say it should, the vacuum energy would be so enormous that the universe would have ripped itself apart in the first fraction of a second after the Big Bang. The fact that you exist, that galaxies exist, that anything exists, means something is canceling out almost all of that virtual particle energy, perfectly, to 120 decimal places, and we have absolutely no idea what that something is. Virtual particles are real enough to push metal plates together, evaporate black holes, and build the mass of every proton in your body. But the deepest secret they hold, why the universe isn't a shredded nightmare of infinite vacuum energy, remains the greatest open question in all of science. Visual note, show a split infographic, left side labeled theoretical vacuum energy with a massive towering red bar graph going off the top of the frame, right side labeled observed vacuum energy with a nearly invisible blue sliver at the base. Label the gap 10 superscript 1 superscript 2 discrepancy in bold. Clean, academic chart style. From the invisible pressure pushing metal plates together, to the slow death of every black hole in the cosmos, to the unsolved mystery that may require an entirely new physics to explain, virtual particles are proof that reality is far stranger, far richer, and far more uncertain than anything your intuition was built to handle. The universe is not made of solid stuff. It is made of flickering maybes, borrowed energy, and questions we haven't learned how to ask yet. Subscribe to Moonlit Minds for daily mind-blowing facts that will change how you see the world.